So thank you all for being here today. You've probably all passed several rivers in your way coming here. Rivers which have their origin high in the mountains of the European Alps. These rivers are fed by glaciers, impressive big bodies of ice, but they are threatened by the climate. And in this thesis I'm going to answer the questions about modeling the effects of mountain deglaciation on the proglacial runoff and channel patterns, and in specific, what is the long-term effect of deglaciation in low to mid-latitude mountains on proglacial runoff and channel morphology, and whether the Badlands model is suitable for modeling glacier retreat, ablation, and runoff over centennial timescales. So, to start off, I'll start by giving a general background about glaciers. Then I'll continue with the methodology, the results, and then finally I'll talk about the limitations and significance and give a conclusion. So first of all, glaciers. You can see an image here from a glacier in Alaska. And we will talk about several important terms which will be used. First of all, the mass balance of a glacier. As you can imagine, on a glacier falls snow, and high on the glacier there's typically a high mass balance, whereas low on the glacier there's typically a low mass balance. So this means that due to this imbalance, the mass needs to be redistributed to remain in equilibrium, which gives the glacier flow. There is a direction of flow. And typically in winter, there's a lot of snow falling on the glacier, whereas in summer, it's mostly melting away, which gives a seasonality to this pattern. This unbalance, which I talked about, of the mass balance, gives a mass balance gradient. So on top of the glacier, there's a lot of new snow coming every year, whereas on the bottom of the glacier, there's a lot of snow melting away. Another important term here is the mass turnover. So the mass every year which the glacier gains, but at the same time also loses while it keeps the same mass. And the mass turnover will be important in this research. And most of the time the mass turnover is very high in warm, humid maritime environments, whereas it's lower in cold, dry, continental regions. So, next on to proglacial rivers. So in front of glaciers, there's typically rivers fed by meltwater. These are highly dependent on the mass balance of the glacier and strongly seasonal, like already said. The most common type of river in front of glaciers is a braided river, which can be seen on the top of the slide. And a braided river consists of several to hundreds of kilometers length of channels and is highly dynamic with a high sediment load and a high discharge. So, next on we'll be looking at landscape evolution models to model these glaciers retreat and ablation. And we'll be using the Badlands model. The Badlands model is a numerical model, so it consists of a bunch of equations and it's forward modeling. So it looks into the future and we can't look into the past. It's using an integrated approach of fluvial environments, coastal environments, and marine environments, and we'll be looking at whether we can also model glacial environments. So, the most important equation from the Badlands model is the stream power law. It's a very simplified version of reality, and it's mainly relevant on large scales, both spatially and temporally. The equation shows that the most important parameters are the precipitation, the drainage area, and the slope. And based on these parameters, the erosion of the landscape will be determined. So that's how much the landscape is eroding away, so getting lower or getting higher, being deposited. From the Badlands model, we'll get two things outputted, which we'll use, and that's the elevation change, so how does the topography change, especially of the glacier, and how does the discharge, so the stream network throughout the area change. So, next on we'll be using a channel pattern model to give an indication about the channel pattern which will form in the proglacial environment. So, we use a channel pattern model by Kandel et al., which is based on statistical discriminators and uses 5 different channel patterns, of which 4 will be relevant in this research. This model assumes that we use the stream power and the medium grain size to determine the channel pattern, and the stream power is based on this equation here and depends mainly on the discharge and the slope of the terrain. So, next to model inputs. For the Badlands model, we require a time structure, so when do we start, when do we finish, and on which time steps do we do this, and we require an initial topography, so with what landscape do we start. We also require the precipitation of the area, and we require the glacial thickness at the start of our time step. On top of that, for the channel pattern model, we use the discharge and the slope provided by the Badlands model, and we need to insert median grain sizes for the model to work. So next on, we'll go to the methodology which we use to obtain the results. So, to repeat, we are answering questions: what is the long-term effect of deglaciation on low to mid-latitude mountains, on proglacial runoff and channel morphology, and we'll be looking at whether the Badlands model is suitable for modeling glacial retreat, ablation and runoff over centennial timescales. So first of all, what I did was I looked at all the glaciers globally from the random glacier inventory, and I determined which glaciers are low to mid-latitudes and which glaciers lie above a certain elevation of 1,000 meters. And those were these regions which are seen on screen and are basically located in the middle here and not at the poles. What I then did, I looked at all parameters of glaciers, so what is their latitudes, their elevation, their size, slope, turnover, their mass loss each year, their precipitation, the response and continentality, and I looked at how they correlate together, but most importantly, how they correlate to the runoff. Well, here you can see all the correlations, but what I found was that, most importantly, the glacier size and the glacier mass turnover was most important in determining the behavior of the glacier in terms of runoff. So what I did, I made 10 different models, 4 different models for each climate scenario, which ranges from a degrees warming of 1.5 degrees Celsius to 4 degrees Celsius. I looked at glacier size, from large to small, about the area, and I looked at the glacier mass turnover, which was high, so a lot of input and melt each year, too low. Then eventually I decided not to model the small glaciers because there were only one grid size on the Badlands model, which wouldn't give any significant results in the end. So, based on these 8 different models, I did the next steps which I'm going to show you for each model separately. I got seasonal runoff data for every month, and I combined this data into seasonal runoffs. So the winter months, you can see they all show a similar pattern of almost no discharge. I combined them into a winter month, and I did the same for spring season, summer season, and autumn season. And based on the model, I extrapolated the projections from 2100 to 2200 or 2300 if the model suggested that glacial response times were longer than 100 years. So based on this, I made Badlands inputs. So the time structure, like I already mentioned briefly, starts at 2000 and models to 2100, 2200 or 2300 in time steps of 1, 2, 4 or 5 years, depending on the time scale and the feasibility of the model, as it took a long time to run on my laptop, and this allowed for quicker computations. Here in the images you can see the topography map, the glacier thickness, so first the glacier thickness map, then the bedrock thickness map, and lastly the topography map, which I used in my models. I also have them for the large glacier size here, which is a significantly bigger glacier, and also a thicker glacier, which was used to input in the model. Lastly, I required precipitation maps, and the precipitation maps consisted of 2 values. One value which was of the glacier, which was taken as precipitation values of typical regions, and I used the runoff curves, which I showed in the previous slide, to populate the area on top of the glacier. So in this case, the precipitation doesn't mean the rain falling, it means the water melting from the glacier in addition to the rain falling. So lastly, for the stream power law, I tweaked it to go from the stream power law for modeling rocks to model ice. So I want a linear relationship on precipitation. So every single drop of water which would fall on the surface is converted to a height difference in the glacier, so that every bit of water which runs off is directly related to snow melting from the top of the glacier. By again a coefficient kappa for the erodibility factor, which is now the melting factor of the glacier. So the Badlands output provided several locations where I took the discharge, because discharge was calculated yearly, seasonally by the model, and spatially over my area, and I took 6 or 7 points on my model where I extracted the discharge from, and I looked at the slope and the channel pattern. So for the channel pattern, I did a Monte Carlo simulation of 1,000 runs, and I used normally distributed parameters like the discharge, the grain size, and the slope to obtain a channel pattern. And why did I do this? If I would only use for every location one discharge value, one slope value, and one grain size value, I would get one channel pattern value. But then it would be a braided value throughout the entirety of the time, and I wouldn't see any change. So I used a Monte Carlo simulation to see the change in river pattern. So, next on, we'll be looking at the results. So based on the channel pattern models, I got these runoff graphs. We'll go more into depth on each separate one later. So in generally, what we're seeing is that it has very close proximity to the runoff graphs which we inputted for precipitation maps. There's an initial increase in summer discharge, after which it greatly drops to lower discharge values. On top of that, there's a high change in seasonality. As you can see, for the different seasons, there are different patterns existing. Some will get wetter, some drier. And we see that for the larger glaciers, there's a relative, we see that if we go further downstream, there's a relative change in discharge as well. As downstream, we get more discharge. So if we look at the climate scenarios, we see that there's relative limited influence. Only later in the century, they get some minor changes in the spring and in summer. Then if we look at the mass turnover types, we see some bigger changes. We see that high turnovers correspond to high discharges, which you can see as the green line, whereas low turnovers have much lower discharges. And we see that there's a lower response time for high turnover glaciers. As you can see, the peak in the summer graph is much wider for the blue graph than it is for the green graph. Then lastly, if we look at the size types, so the medium glaciers and the large glaciers, we can see that there's much higher runoff for larger glaciers, and on top of that, for larger glaciers, there's a higher peak discharge variation, as the peak is much more distinct for the large glaciers. This, however, is proportional to the glacier size. So, if we look at the discharge over distance, so from the glacier terminus all the way downstream to up to 40 kilometers, we see that discharge is continuously increasing, and there are several jumps in discharge. This jump is due to two rivers coming together, giving a high peak jump in the discharge. So if we look at the climate scenarios, we once again see that there's very limited change in discharge. If we look at the mass turnover, however, we see in addition to high mass turnovers having a much higher discharge, we also see that, which is more difficult to see in the image, but we see that the relative importance of the runoff of the glacier is much important for low runoff glaciers. So what you need to think is that the gradient of the line up to 0, so the glacier terminus, is steeper relative to the slope after the 0 point, so after the glacier terminus, where the river is only fed by additional rainwater and not anymore by additional glacier melt. Lastly, if we look at the glacier size, we see the same thing, that for very large glaciers, the importance of the glacier is much more important, as up to 0 there's a much steeper gradient. So, when we look at the channel pattern, which was calculated, we see that over time the channel pattern barely changes. We go from 92% to 96, and from 93 to 98 for the different sizes and the different climate scenarios. But we do see a relevant change for the low mass turnover scenario, where there's a 10% change in channel pattern. So we can say that only for low mass turnovers, the melting of glaciers has a significant impact, or a more significant, still very small impact, but a more significant change in the channel pattern at the glacier terminus. However, this is all plotted for the glacier terminus. If we move further downstream, we see that this influence greatly decreases, therefore saying that for channel patterns it isn't really relevant. If we plot them over distance, we can see this, and we see that for the light blue line in the middle, for the low mass turnover, it steeply drops from about 95% braiding to only 40% braiding, whereas the other graphs all stay at a much higher probability of braiding. Yeah. On top of that, we also see that smaller glaciers, also further away from the terminus, drop much quicker in their amount of braiding. So they will revert quicker to a meandering river shape compared to a braided river shape. So, lastly we'll be looking at the limitations and significance of this research. So, we'll be looking at the Badlands Landscape Evolution Model, of which an animation is shown on screen, and it's very much simplified. So we relate precipitation directly to erosion, or glacier melting in this case, which is not how the actual world is working. We do not have any glacial retreat, even though it might seem like the terminus is retreating, it's just because the tip is much thinner than the main part of the glacier. On top of that, the erodibility coefficient had significant errors. We assumed the bedrock around the glacier to not erode during this time, so we gave it an erodibility of 0, but then the model didn't function anymore. So I had to give it an as low as possible erodibility, which still gave the terrain an erosion of 14 meters. Far too much, but since it's everywhere the same, you don't see it in the relative topography change. On top of that, I assumed complete deglaciation, but probably at the end of the century there are still some parts of the glacier left. And if we assume a whole mountain range which is completely glaciated, there's probably much more ice than I've modeled in my simulations, which would also make the impact for downstream discharge much bigger. And lastly, for the channel pattern model, I assumed constant discharges instead of seasonally varying discharges. Then what can Badlands do with this research? So what's the future of Badlands in trying to incorporate glacial environment? So firstly, I would say split up your bedrock from your glacier. At the moment, I modeled the rock in the same way as the glacier, which obviously isn't true. So there should be a separate class for glaciers compared to rocks. On top of that, I would suggest an ice-to-water volume conversion. So every volume of ice, in this case, which is eroded, should be converted into runoff at the same time in the model, and not me doing that in a precipitation map to somewhat match the results. And on top of that, to get glacial retreat in, I would suggest getting elevation-dependent melting, so that the tip of the glacier, which is lower elevations, melts quicker than the top of the glacier. And lastly, research has shown that you can use glacier power laws, similar to stream power laws, to model glacial erosion, which uses the snow accumulation instead of precipitation, uses the catchment area of snow instead of water, and use the ice surface slope to model the erosion that the glacier causes. So, now to conclude my research, we looked at how the runoff changes due to the deglaciation of mid to low latitude mountain regions. And we see that there's a short-term increase in runoff, especially in summer, and after that, no long-term change annually. But there is a large change in seasonality. Summers and autumn will get drier, whereas winters and springs will get wetter. And this is especially relevant for low mass turnover glaciers, where the region is typically arid and has a much bigger dependence on glaciers. On top of that, we saw that mostly mass turnover and glacier size influence this runoff. Then for the proglacial channel pattern, we saw that there's basically no significant change. Only for the low mass turnover, there's a bit of a significant change, but still you would say it's not too big of a deal. However, if we look at the change in braiding or channel pattern further downstream, we see that it drops significantly quicker for low mass turnover glaciers and smaller glaciers. And lastly, for Badlands Landscape Evolution Model, we would say that currently it's unsuitable and unreliable to model glacial environments. But with the improvements of the separate glacier class, ice-to-water volume conversion, an elevation-dependent melting, and a glacier power law, this would probably greatly improve the model's performance. And with that, I would like to conclude my presentation. If there are any questions, feel free to ask.
Yeah, Theo, thank you for your presentation. You studied the effects of the climate change on the glacial runoff. Have you also taken into account the effect that that climate change has on the area surrounding it? So I can imagine the soil properties changing.
Yeah, so based on precipitation, at this point, since my focus was on glacier runoff, I said to not make the model too complex and not being able to focus on one little thing, I said the surrounding precipitation will be the same over the model timescale, but I did change it seasonally. So in winter and summer there is a difference, but this difference is the same throughout the entire time scale. So I didn't change it in that respect. But yeah, if you want to have an accurate model for a specific case study in a specific region, you would of course have to look into how that's changing. Okay. Did it answer your question? Yeah,
because that was my second question. I saw the precipitation was 1.4 meters per year or something all the way around.
Yeah.
Say if you would, if you go back to it. Yeah, that's the yellow, so it was 1.4. Yeah. Say if you would take into account, for example, soil generally being drier, less saturated because of a warmer climate, how would that affect your runoff patterns?
Yes. So in my case, it wouldn't have any effect at all, because my assumption was that in my 300 years, the entire region would not erode. So in the scope of this study, there wouldn't be any change. If you would take into account, still for the Badlands model, the runoff, it wouldn't change. But if you want to compare sediment flow, so the sediment output of the river, it would be relevant. So it's something I didn't do in this research, but I have been thinking about. My whole glacier mass, if it erodes, it also produces sediment. So at this point, I just said, I'll ignore that. But at downstream of this river is now lying a whole glacier, which obviously isn't the case, because a glacier is ice, and ice is water, it's not sediment. So yeah, that's definitely something to improve on, and that's why I said for getting a separate glacier class, which doesn't produce sediment, so your original model is still functioning, which due to all my tweaking around isn't anymore.
Yeah, okay, thank you.
Yeah, thank you. Mark.
Very nice presentation, thank you. You make a few assumptions, quite a few, but which of these assumptions would you say is most questionable, and how, due to your limitations of the research, of course you have to have some limitations, but how would you address these most questionable assumptions in further research?
Yeah, so I think the main problem, which I think the power of a model is to predict what's going to happen in the future. What I did, I gave the precipitation relation, so erosion is related to precipitation, and then we get melting. So the biggest assumption I really made here is that I still kept using the original erodibility factor, which is actually directly related to the runoff, which is the case here. So I had an iterative approach in determining which erodibility factor fits my thinning glacier. So for future research, if you want to get rid of this assumption and get like the predictive model to do its thing, you want to link your mass loss of the ice to the runoff, so that you wouldn't have to, so that you get like a direct conversion from ice to water, and you don't have your problem of an erodibility factor, because an erodibility factor for ice is not a useful thing. Did I answer your question? Yes. Any more questions? Yeah, Casper.
Yeah, so if I understand correctly, you try to model glaciers using the Badlands model, which does not have inherently a glacier modeling function.
Yeah, exactly.
Did you test your model with historical data, or did you consider doing that at any point?
So I didn't. So it is basically just trying to work out whether I can make a glacier which somewhat behaves like a glacier. So the values I used, they are actually existing values, but the glacier I put in it, I just made up myself, and then just run the model and see what happens. And then you see, well, it only thins. It seems to retreat, but that's only because the tip is thinner than the end. So in this case, it's just looking at how does it function, how could it be used, and then the next step indeed would be, if we would have a case study, we would take a glacier in the European Alps, for example, and try to model that. How can we make it an accurate representation? So if you take data from 1950 to 2025, see if we can match that. So that would be a next step, but yeah, not the scope of this thesis yet. Did I answer your question?
Yes.
Mark.
If I understand correctly, you didn't account for glacial isostatic adjustments?
Yeah, no, I didn't. I left the isostatic rebound to be what it is.
So what would the implications be if you would incorporate it in your research, and how significant would it be on the timescales you consider?
So this is because my erosion at this point is messed up. It wouldn't have much influence at this point, but in the future, it would definitely be useful for your sediment output of your glacier. So your aesthetic rebound, like your uplift you're getting, and then if you could compute correctly your glacier erosion, then it would definitely have an influence, because due to the isostatic rebound, you would probably get more erosion, which could erode, which would get more accurate results. Yeah.
Do you know what kind of scale that is? Like
Ooh, I wouldn't have a clue about that. So I don't know. You should ask Robin. He's not here. He looked into that.
Right? If you're done, then that's our turn.
Yeah.
Thank you. Oh, no worries. So we have good news. you do pass. So yeah, thank you, Timo, for the presentation, for answering the question. We are really impressed by how capable you are and how well you understand your topic, and that's something that definitely deserves a high grade. And we spent all the time we were there, we were trying to find something wrong with your thesis, so we cannot find anything. So we decided to give you 9.5 for your thesis. So we're three people grading your work. Maria, I think, cannot be here, she's on holiday, but the two of us definitely agree on the grade. And the results, how you interpretation of the results, as well as the presentation, we both agreed to give you 10. So 10 is possibility left. Just and overall, very pleased. The one comment we agree on is that it's beyond expectation. But that's also 10 weeks ago, when you knocked at our door saying, I want to do a thesis with you. We were like, but bring it on. I do want a challenge. I just want something that is meaningful, and I want to do research. And we did deliver just that. We were just saying that it feels like talking to a PhD student sometimes.
And like a third-year PhD, not like a first year.
Definitely, we hope you stick with us for the master, but I don't know what your plans are.
Well, I am sticking with the master.
Okay. Good news for us. And again, I just want to say it was a pleasure working with you and us.
Thank you.
Both of us.
Thanks. It's a pleasure working with you too.
Cool.